when we need to run A/B tests to show that the treatment is no worse than control, it's incorrect to run a regular A/B test. Non-inferiority test is designed for those use cases. Hi, everyone. Thanks for coming to my presentation. My name is Max. Today, I'm going to talk about non-inferiority test in A/B testing. The title for today is Absence of Evidence is not evidence of absence. So this non-inferiority test is particularly useful when you need to roll out a neutral feature. A neutral feature is a feature that is expected to have no impact on the business metrics. Before diving in, let me introduce myself a little bit. I'm a statistician by training. After getting my Ph.D. in statistics, I moved to the Bay Area and worked in different tech companies. Currently, I'm at Wish. I've been working in the space of machine learning and experimentation as well. This non-inferiority A/B test is one of my recent projects. Here's the agenda for today. First, I'll cover when this non-inferiority test is useful, and then what non-inferiority test is, followed by how is non-inferiority test better than regular A/B test. Lastly, I'll give a conclusion. So when is non-inferiority test useful? I'm not claiming that you should stop running conventional A/B tests altogether and start doing non-inferiority test. But in some cases, the conventional A/B test could fail, and it makes sense to apply non-inferiority test.
This is Romo Santiago from Experimentation. Every week we share interviews with and conference sessions by our favorite conversion rate optimizers from around the world. So if you like this video, smash that like button and consider subscribing. It helps us a bunch. Now back to the episode.
Here are some use cases. For example, a pharmaceutical company has a new generic drug that costs only 10% of the brand name drug. If the company could prove that this generic drug, the efficacy of this generic drug is non-inferior, then that would be good news for the patients. Another example is an e-commerce company is evaluating a new policy, for example, to take down misleading products. And it's clear that this new policy can boost customer trust. If they could show that this new policy has no negative impact to the business metrics, then it would be a no-brainer to introduce this new policy. The third example is, say we have a machine learning model in production, which is complicated and computationally expensive to run. On the other hand, we have a simpler model that is easier to maintain and much less expensive to run. If we could show that the simpler model is no worse than the complicated production model, then we are confident to replace the production model by the simpler model. So does conventional A/B testing work in those cases? Let's take a look. Let's devise our decision rule as follows. We run an experiment and conclude there is no difference between treatment and control when the p-value is larger than 5%. It looks like the decision rule makes sense because when p-value is smaller than 5%, we could conclude that there is a difference between treatment and control. But is this decision rule correct? The short answer is no, because absence of evidence is not evidence of absence. When the p-value is larger than 5%, it simply means that we don't have enough evidence to make any conclusions. Furthermore, if the decision rule was p-value larger than 5%, then how long should we run the experiment? How do we even calculate the sample size? Let's look at this plot. So this is from a simulation study. And because it's a simulation study, we know that the treatment is actually worse than control. The x-axis is the number of days we run the experiment. This red line indicates 5% error rate, and y-axis is error rate. As you can see here, the shorter we run the experiment, the higher the error rate. If we stop the experiment after we run it for 1 day, then the probability of making a mistake is higher than 80%, right? So the mistake means that we'll say that the treatment is no worse than control, but the treatment is actually worse. So what is wrong? Let's look at it from a statistical perspective. This study is a little heavy in theory. Don't worry if you cannot follow it. It shouldn't affect your understanding of the whole presentation. So for typical A/B testing, the null hypothesis is that there is no difference between treatment and control. When we get a p-value smaller than 5%, we could reject the null hypothesis and conclude that there is a difference between treatment and control, right? We never accept a null hypothesis because when the p-value is larger than 5%, it basically means that there's not enough evidence to make any conclusions. Again, absence of evidence is not evidence of absence. Furthermore, there's a distinction between statistical significance and practical significance. So if there is a teeny tiny difference between your treatment and control, say the difference is like 0.000001%. If you run your experiment long enough, you will eventually reach the statistical significance, meaning the p-value would be smaller than 5%, and you conclude that there is a negative impact. But do you even care when the negative impact is that small? Probably not. But conventional A/B testing doesn't have a framework to take this practical significance into account. Now, hopefully I've convinced you that for some use cases, when we want to show that the treatment is no worse than control, conventional A/B testing simply doesn't work. And non-inferiority test is designed for those use cases. Conceptually, the non-inferiority test is actually pretty simple. We change the null hypothesis to be the treatment is worse than control. Now, when we have a p-value smaller than 5%, we get enough evidence to reject the null hypothesis and conclude that treatment is no worse than control by a margin delta. So this delta here indicates practically significant difference, say 2%. And in essence, this non-inferiority test is a one-sided test with a delta. So you may wonder, does this small change in null hypothesis make a big difference? Let's look at how non-inferiority test is better than the regular A/B test for those use cases. So let's compare the regular A/B test versus non-inferiority test. The decision rule for regular A/B test is, p-value larger than 5%. And the decision rule for a non-inferiority test is the p-value smaller than 5%. Please note, these two p-values are calculated in different ways. Let's compare non-inferiority test and regular A/B test in this simulation study. In this simulation study, we know the treatment is indeed inferior. So in this plot, the x-axis indicates the number of days we run the experiment, and y-axis is the error rate. The orange dots are for regular A/B tests, and the green dots are for non-inferiority test. So the first orange dot here indicates that when the treatment is indeed inferior, there is a higher than 80% chance a regular A/B test would incorrectly claim that the treatment is non-inferior. The longer we run the experiment, the lower the error rate for the regular A/B test. On the other hand, for non-inferiority test, the false positive rate is well controlled below 5%, regardless how long you run the experiment. Again, this is caused by that we make conclusions when p-value is larger than 5%. Absence of evidence is not evidence of absence. Let's compare the two types of tests in another simulation study. In this simulation study, we know the treatment is indeed non-inferior. And again, in this plot, the x-axis indicates the number of days we run the experiment. But the y-axis in this case shows the true positive rate, i.e. the power. For regular A/B test, the longer we run the experiment, the lower the power. This is because when we run the regular A/B test for a really long time, it tends to get statistically significant due to a practically non-significant difference. On the other hand, for the non-inferiority test, the longer we run the test, the higher the power. It aligns with our expectation for the power of a typical test. In conclusion, when we need to run A/B tests to show that the treatment is no worse than control, it's incorrect to run a regular A/B test. Non-inferiority test is designed for those use cases. Also, we are in the process of open sourcing our Python library for A/B testing. It's called WishAB, which supports the non-inferiority test. So please stay tuned. Last but not least, I want to thank my colleagues, Pavel and Pai, for their support along the way. And also, I want to thank Tab for providing the use case that motivated this study. I also have some appendix slides to show the differences in decisions between regular A/B tests and non-inferiority tests under different scenarios. Also, what would happen when you run a regular A/B test with more sophisticated decision rules? In essence, even with more sophisticated rules, the problems are still there. You can reach me by email or on LinkedIn. If you are interested in those slides, here's the URL. Thanks for coming, and please let me know if you have any questions.